Thank you, everyone, for being here. Thank you, Damien, for the great introduction. My name is Charlie Ice. I am part of NXP's wireless MCU team, and I'm really excited to talk to you today about channel sounding and focus in on, as Damien mentioned also, how to use multiple antennas to improve the accuracy of the channel sounding measurement. And my goal for this presentation is that at the end you walk away being able to know kind of the basics of how to implement this in your system. You also understand how the channel sounding standard itself supports this, and then also kind of what to look for when selecting an algorithm for your end channel sounding designs. And this is really going to be followed up by Lambda 4. They have a lot of good information about kind of implementing this in the channel sounding algorithm and showing some more data. So it's really a tag team effort here. And the way this we'll do is I'll look a little bit more about applications and the vision. Damien talked a lot about that, but I'll just kind of go through that again and kind of pick one example in particular. And then we'll look at the hardware piece. How are we actually getting the hardware set up to do the multiple antennas, and what are the hardware implications that are kind of happening in the physical world? And then we'll shift gears and look at the software side. How is the channel sounding spec allowing the algorithms to use multiple antennas and take measurements across those different antennas? And then, of course, we'll wrap up by showing some examples of how that's done in some real-world designs and some reference designs that NXP has to offer. So just in general, channel sounding is really ushering in what we like to call ambient computing. And the idea is that once you know the distance between two devices, it doesn't take a lot of leaps to then know where those devices are. And once you have location, you can have a huge amount of automation. So for example, if my conference room in my office has Bluetooth channel sounding and it's paired with my phone, I can walk in with my phone, it knows who I am, how I want the lights, how I like my PC set up, and so potentially the IT equipment, the air conditioning could all be configured right when I walk in the room. And that's all based on simple Bluetooth channel sounding. So a lot of automation there. Or my desk at my office could know that based on channel sounding that I'm really close, so it turns on the monitor, it turns on the dock, and I just put my laptop down and everything's ready to go. There's no plugging in cables, there's no hoping it boots up, it just both talk together and are automatically up and running. So really interesting things. Again, kind of smart homes. You can think of a lot of other smart home things that could happen based on this, and again, the smartphone knowing where you are in the home. So that's the motivation. Again, that kind of idea of ambient computing and knowing where you are. So of course, by improving the accuracy, you can improve that location awareness, and multiple antennas is one of the best ways to do that. And one of the other examples that we touched on earlier that I'm going to use in this presentation is car access. And so in this example, the car, you have a key fob, and the key fob has channel sounding as well as ultra wideband. And as you walk up to the car, channel sounding is used to do kind of the initial ranging. It's Bluetooth, so it's very low power. And you walk up to the car and channel sounding is happening. And then once you get very close, ultra wideband can kick in to do real fine ranging that might be a little bit more power hungry. And so the overall user experience is improved because you have now low power from the Bluetooth channel sounding and then super fine, very accurate ranging with ultra wideband for that last bit to know when to unlock your Ferrari securely. And then channel sounding really, it's interspersed with Bluetooth data traffic. So it's not a separate operation that's happening in some strange channel. It's just part of Bluetooth data now. So it fits within the standard, and it's not having to be a separate thing, as we kind of also alluded to. And the nice thing too is that it's part of the standard. So it is fully interoperable. Devices that support channel sounding from multiple vendors will work together and be able to do measurements. There's not going to be any hoping that the two devices from two different vendors are going to work and play nice. Because it's part of the spec, they will play nice. Now, two key things. The first is that both devices do have to be paired to do a channel sounding procedure today, and that's for security reasons. So they do have to be paired and connected. It's not like RSSI where they can just send out some advertising packets. And the second key piece is Bluetooth channel sounding is an optional part of the Bluetooth standard. So both devices have to support channel sounding. So when I talk to customers, a lot of times they say, great, if I have a Bluetooth device, it'll just do channel sounding. And the answer is not quite. You have to make sure that both sides do support channel sounding, and it is an optional feature. So keep that in mind. What we think is, as smartphones adopt channel sounding, that'll become less of an optional feature and just part of and more of a standard feature. But today it is definitely is certainly an optional feature. And channel sounding, as we talked about, does do two different ranging methodologies. So the first ranging methodology is round trip time. And this is really all about how do I make sure that my ranging is secure. And there's a lot of different security built into channel sounding. This one is here as kind of one of the foundational ones. It's timestamps packets being exchanged between the initiator and the reflector. And because those are encrypted packets, it's very hard to hack that. It's really hard to do a man-in-the-middle attack and spoof that or tweak the signaling. This is pretty secure. But you can imagine it's not all that accurate. So phase-based ranging is there to do fine ranging. It's measuring phase shift between tones that are sent between the initiator and the reflector. And then by calculating that phase shift, it can determine the distance quite accurately. But this certainly, theoretically, could be vulnerable to some very advanced attacks. And there's a bunch of things built in here that reduce those vulnerabilities, but it's in theory possible. So the algorithm looks at both and says, if this is very different than this, something went wrong, and we're under attack, throw those measurements out, right? For the purposes of looking at using multiple antennas to improve the range, we're going to focus just on phase-based ranging. Because if you think about sending packets with timestamps, those are basically data. There's not a lot that multiple antennas are going to do to make that more accurate. But for phases, we're measuring phase shifts. Multiple antennas will make a big difference here. And then we'll see more about the data side of that with Lambda 4. But this is where we're going to focus. And channel sounding includes support for this in the spec, only on the phase-based side. So this is where we'll look for the rest of our presentation. But keep in mind there are two different methodologies that are happening. So with that, now let's dive into kind of the how. What's happening on the hardware side? What's the RF side? What's going on in the more real world? And then, like I said, we'll take this and look at what's happening on the software side. And much like any RF topic, you can go super, super deep, lots and lots of math. I'm going to give you the kind of higher level, so you can then go read some of those papers and understand what they're talking about. So, like we talked about, we're sending tones back and forth. In this diagram that I have here, the initiator has sent some tones, and the reflector is sending those tones back. And the main thing that causes a lot of the inaccuracies here is reflections. So think about this room. If my pointer is transmitting, there's a lot of signals bouncing off the ceiling, the floor, or if it's in my back pocket, now you've got reflections off of me, potentially off of the walls behind me. So that's what's really causing a lot of the issues. And in this simplified diagram, you can see the line of sight signal is the blue signal, and that's what we want to measure. The other two signals, the orange and kind of the lighter orange, are the reflected signals, and those are causing interference and making things less accurate and making our ranging kind of throwing us off. And so our goal is, how do we really get the most out of that blue signal? How do we isolate that blue signal and measure just that? Well, one of the best ways is through multiple antennas. And this is what we call antenna diversity. I'll use those terms interchangeably, but in a lot of the papers you'll see they call it antenna diversity. And so if we had to have two antennas on the initiator that's receiving the reflected signals, now the first antenna at the top, you can see it actually is getting most of that blue signal. So the signal strength of the blue signal is maximized by the top antenna, and the second antenna is receiving most of the reflected signal. So if we did a really simple algorithm, we could say, which antenna do I pick to do my measurements off of? I'll pick the antenna that has the highest signal strength based on the two, and that's probably the one that has the line of sight signal. I'll do all my calculations off of that. There's a lot of other ways to do that are more advanced, but that's a really simple way you could look at what's being received and go, all right, how do I pick the two antennas? I'll pick the one that has the highest signal strength. And you can have multiple antennas on both the initiator and the reflector. So this is what we call a 2x2 situation. So there's one on each side, two on each side, and we'll cycle through each antenna pair. And again, our simple algorithm here is just going to say, well, which of those four paths had the highest signal strength? And we'll just guess that that one, therefore, is the one that actually has the line of sight signal, and we'll do our calculations based on that. And you'll see that, as Damien mentioned, that the Bluetooth spec does allow for multiple antenna configurations, multiple paths. I'm going to focus on the 2x2 configuration here that I've drawn, because that one we've found in our experiments tends to be the best balance between performance and cost. It does require that you control the antennas that are on both sides, but in our key fob example, the car manufacturer would be able to have 2 antennas on the key fob and 2 on the car, and therefore be able to implement this and then have that kind of a good balance and trade-off between performance and cost. So before I leave this, kind of nod of heads, you guys with me, or is this kind of going too quick? All right, I see a couple heads and some thumbs up, so we're going to keep going. So the first thing that we're going to do on our hardware PCB design is what we call spatial diversity. So when you see PCBs that have, and we'll see one in a moment, that have multiple antennas, the antennas are spaced out. And they're spaced out because that way, each antenna, no matter how much phase shift happens, is always going to be receiving more or less the peak signal. And we'll space them out by at least half a wavelength. And so you can see the orange signal here is that shifted signal. And so now, as it gets shifted, antenna 2 gets kind of the peak signal. Antenna 1's not getting the peak signal anymore. If it keeps shifting, you'll get antenna 1 having more signal strength than antenna 2. And so by having them separated out physically on the board, we're going to maximize the reception. Now likewise, angular diversity is the angle of the antennas themselves on the PCB. And so if we take a typical PCB antenna, say an inverted F, which is used across, very, very common in Bluetooth designs and in 2.4 designs, this has a radiation pattern of really a donut. It's a monopole. And that's really the goal of most PCB antennas, is to be a monopole. If we slice that in half and do a 2D projection, it looks roughly like this. And this is just kind of for visualization purposes. Obviously, it's pretty crude representation. But if we have 2 antennas and we angle them, now our coverage of those 2 antennas, because they're angled, is much, much greater. And so that's why you'll see on the PCBs that they're not only spaced out, but the antennas are angled at a particular angle to maximize the coverage of that radiation pattern of those antennas. And so if we combine those together, you can see here is one of NXP's channel sounding boards for our KW45 MCU. And this board, you can see the antennas are up on the top. There's 2 chip antennas. They're spaced more than half a wavelength, but multiples of half a wavelength. And then they're also angled. And so we achieve both the angular diversity and that spatial diversity on the PCB with these 2 antennas. Now, there's also an RF switch on this board. And the reason for that is our device only is designed to receive on one antenna at a time. And so we use the RF switch to switch between each of the 2 antennas throughout the channel sounding procedure. And then finally, the last piece is, as Damien mentioned, channel sounding doesn't provide the Bluetooth channel sounding spec doesn't provide an algorithm. So your algorithm that's running to take the measurements and turn them into a distance number has to be able to use multiple antenna information. And so our device, we include an algorithm from NXP called the Rapid and Accurate Distance Estimation. It's very cleverly named, or RAID. And RAID takes multiple antenna information and combines that into a distance measurement. And that's something that for you when you're designing your systems, to pick a partner that has good algorithms for channel sounding. Lambda 4 has very good algorithms as well. They're also one of our partners. So when you're designing, you can pick an algorithm from either NXP or a partner like Lambda 4 or any silicon provider. Make sure they have a good algorithm that, of course, uses multiple antennas. So then now let's look about how is the Bluetooth spec actually implementing this? What's the software behind this that makes it work so we can take those measurements across multiple antennas? So as we already talked about briefly, the channel sounding spec does include services. So it includes a client and a ranging server. And the idea is the ranging client's going to be doing the actual distance algorithm on this piece, and then the ranging server is going to set up that channel sounding procedure. So this is going to tell the ranging client, I have these features, I can implement this security, I can implement this number of antenna paths, and really set up that whole ranging session. And keep in mind, it's really flexible. So they can be the central or peripheral, they can be the initiator or the reflector. So it's not necessarily dictated which one is which. You have to they determine that when they do their negotiation. And like I say, I think, and so for example, here's how that would look in our car example. So in our car example, the key fob here is our server. So it's going to have all the information about what it can do. And then the car anchor is going to be that client. And the car anchor is going to be running the distance algorithm, but it's not necessarily going to be the initiator and this is going to be the reflector. That's really up to the two's negotiation, right? But this is going to do the algorithm, and this is going to just be setting up that ranging procedure. And then from a kind of step-by-step procedure, you'll see channel sounding is going to start out with a discovery procedure. What procedures do we have? And then the Bluetooth spec talks next about how do I configure the devices and what security do we both support, because there's different levels of security that the devices can support. So they negotiate and understand which ones do they support and how do they run those different levels of security. And then the spec actually then has them do the channel sounding procedure, measuring the channels, round-trip time, round-trip phase. And then finally, they exchange data, because again, it's the initiator and reflector can be the client or the server, and so they have to exchange data based on which is which. And then the last step is turning all those measurements into an actual distance. And again, that's not part of the Bluetooth spec. That is up to you or your partner or providers to give you that algorithm. And so we're going to zoom in on the channel sounding procedure itself, and I'll show you how that's using multiple antennas and how that's implemented in the channel sounding procedure. We're going to talk primarily about this box, but just keep in mind there's other steps in that overall procedure. So this is a little bit busy, so let me walk you through this. This is what's going on with that channel sounding procedure. This is what's showing you underneath what is it actually doing. And the channel sounding procedure is broken up into events. And so there's multiple events per procedure. And then each of those events is broken up into a sub-event. And the sub-events are broken up into steps. And between each step is a frequency hop, because the algorithm we don't want to interfere with others. And we want to make sure that we can measure, take channel sounding measurements across the whole frequency range. So there's a TFCS, which is the time for frequency hopping, and then there's a step. And there's multiple steps per channel sounding procedure. And so if we go back to our previous diagram of showing how Bluetooth channel sounding is interspersed with data traffic, you can see actually what we're talking about is it's actually just events. So the channel sounding events are interspersed with data transfers, and multiple events are interspersed between data to make up a complete channel sounding procedure. So we're combining multiple events interspersed with data to make up that complete procedure that we're going to have for the full measurement range. Now, each step, as I say, each sub-event is made up of different steps, and each steps can be one of four things, and the four things are called modes. And so the step could be mode 0, which is calibration, mode 1, which is our round-trip packet exchange, mode 2, which is phase-based ranging, or mode 3, which is combining the two together into a single step. And so each step, so we have step 1 here is mode 0. We could have step 2, which is, say, mode 1. Step 3 would be mode 2, and just so on and so forth. But each step is only one of these four modes. So it's very defined what each step is going to be. They're one of these four modes here. So as you can guess, we're going to talk about mode 2, because mode 2 is the phase-based ranging. Mode 3 combines the two, and so it's once you understand mode 2, you can combine the two pretty easily. So to start off with, for mode 2 with phase-based ranging, and again, we're going to look at the scenario where There's 2 antennas on each side. We're going to start with a frequency hop. That's going to be our modus operandi. We always frequency hop whenever we do a new step. So we'll do frequency hop, and then the initiator here is going to transmit to the reflector, and it's this first signal path right here, the 2 blue antennas. And so this is called antenna path 1, or AP1, here in the diagram. And so we'll transmit and measure the phase. And then again, we'll switch the 2 antenna paths, and then measure again. And then switch again, and switch again. So then we've gone through all 4 antenna paths. So you can see we cycled through the different antenna connections, and we've had a time between each so that the 2 devices can catch up and switch. And then the last piece you'll see, and then between each of these, we're sending the same data. So it's always the same tone each time for each of these procedures, each of these steps. And then finally, the last step is what we call tone extension. This is optional. It's there for security reasons and also to help with regulatory compliance. Sometimes, because we're sending tones, we can run into some issues with FCC compliance. This helps with that, but it's also an optional thing. So the two sides negotiate, and security-wise, they can decide we will send this or we won't send this. And if you're a hacker, you wouldn't necessarily know if it's going to be sent or not. And so this is a kind of easy indication of, I got a tone extension, but I wasn't expecting it. Something's wrong. I should throw these measurements out and start over. And then transmitter ramps down. It's time for that. And then the spec has time for them to switch roles. So now, and this is where that data measurement exchange is so useful, is we're actually going to be flipping who's transmitting and receiving. So now the reflector is going to transmit to the initiator. And so we'll do the same steps, just reversed. So now these top 2 antenna paths are the 2 we're going to be looking at. Then we'll look at antenna path 2, which is this one, antenna path 3, and then antenna path 4. Again, we'll cycle through all those antenna paths with the roles reversed in terms of the transmitting and receiving. And then finally, there's again a tone extension. So we'll do that or not, optionally, between the 2. And then we'll ramp down between the 2 devices. So that's the complete procedure for multiple antennas. This is mode 2, so it's the phase-based ranging. This also can be combined with round-trip time with mode 3. So then, our distance estimation algorithm is going to take all that information, because they're going to do a data exchange, and it's going to turn all that magically into a distance measurement. And say the distance is 5 meters, 4 meters, 10 meters, whatever. And again, that's not part of the channel sounding spec, so it's key that whatever vendor you pick, whatever partner you pick, has that algorithm that can take those multiple antenna measurements and turn them into an actual distance estimation. So again, our kind of initial thought of how you would do that, very simplistic, would be which one had the highest received signal strength out of all those 8 measurements. Certainly, there's a lot of ways you could make that more complex, but that's just kind of to visualize how could this be done. It's a simple way that could work. And then finally, from NXP, how would you get started? This is a board we saw already, but this is our initial channel sounding reference design with our KW45 automotive Bluetooth MCU. This is an early design for prototyping purposes. It's actually not compliant with the spec, but it does run the channel sounding procedure. We have a device coming out in the future called the M6W72, as well as the KW47 device that will be compliant with the spec completely. There were just a couple security things we couldn't do on this initial silicon. This is a great way to get started, though, to just prototype and experiment and see what the range is like. It can run different algorithms. And then we also have an accelerator for running the algorithms built into the M6W72 that's coming out. It's a customized DSP just for channel sounding that's designed to accelerate the algorithm. Because as you can imagine, as you have multiple antenna measurements, the algorithm can get more and more complex and can take more and more time to run. So our accelerator allows you to run the algorithm faster because it's a customized DSP, but it also could let you run the algorithm multiple times over the same data set, and you could compare those measurements and average them together. So with that, please visit us at our booth if you'd like. We have some really compelling demos. We also have the Freedom Lab, which is a separate booth designed to let you actually run NXP examples on actual devices and get some boards from NXP as well. So, thank you very much. I appreciate your time and look forward to your questions.